All right, we are back and better than ever. Today we are talking about the binomial distribution. The binomial distribution can be, put that back, can only been used when we are sampling with replacement. Okay, that is, I don't know, we draw a marble from a bag and then we put it back before we do our next experiment or our next draw of marbles. We cannot use a binomial distribution if we do not replace. That is beyond the scope of our course. So, it is good. Binomial experiments and the binomial distribution is only good if we are doing an experiment with two possible results: success, like drawing a blue marble, or failure, not drawing a blue marble. Okay, very simple. That's the only time you can use a binomial distribution. And they're very, very powerful, makes life very, very easy. And we're going to repeat the experiment a number of independent trials. We call that a binomial experiment. Again, two outcomes, and the probability of success must be constant for all the trials. And if we say that that success is p, then failure is 1 minus p. In other words, the success and the failure obviously must add up to 1. And the random variable x is the total number of successes in n trials. Okay, a lot of talking to start off, but then we'll get to doing something. But it's really important that you have your head around this, because once you do, it's really pretty simple. It's not that bad. So let's talk about a spinner that has 4 equal sections, 3 blue here and 1 white. And we're going to say that the success is spinning a blue. We don't know how many that is yet, but just for argument's sake, we'll say that the success is spinning blue. And so the probability of spinning a blue on this spinner is 3 out of 4, and white is 1 out of 4. So what are the possibilities if we twirl the spinner 3 times? Well, we could get blue 0 times, we could land on blue 1 time, 2 times, or 3 times. Those are my little x's right here. When you see the probability that x equals little x, these guys are all of my little x's, and you kind of see that right here. Little x, little x, little x, little x. That can be a bit confusing sometimes. Okay, so nice little tree diagram here of all the probabilities. I wish they had started with the 3 blues, and I'll tell you why on the next page, but very simple. We've done this before. Probability that all 3 are white on the spinner. Let's see, we would have to look for white, white, white on the diagram. So white, 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 1/4 times 1/4 times 1/4 is 1/4 cubed, and on down the line. 1 blue and 2 white. Well, there's 3 ways for that to happen, and it's where the green check marks are, just as an example. Blue, white, white. That's 1 blue and 2 white. So 3/4 times 1/4 times 1/4, or 3/4 times 1/4 squared. Same thing happens along this vein here. Boom, boom, boom. 2 whites, 1 blue. And along here, boom, boom, boom. 2 whites, 1 blue. Okay, almost ready for an example. Now, note that this is just this rewritten. Okay, I'm sorry, right over here is what it came from the previous page. Notice, and we're going to work from the bottom up here, because we had said that what we wanted the success was blue. Spinning blue. Okay, and so here we go. If we start down here, the probability that we get 3 blues would be 3/4 cubed. Right down here. This comes directly from the tree diagram. Before I forget, if you don't have your calculator out, pause this video and get it out, because you're going to need it. Okay, I'm glad you have your calculator. Very good. Probability that x is equal to 2, in other words, that we drew 2 blues, is this. And again, 3/4 squared times 1/4 times 3, and on down the line. Notice the 3 choose 3, 3 choose 2. These are the coefficients. 3 choose 0. This is equal to 1 if you remember. This is equal to 3. This is also equal to 3, and this is equal to 1. Again, the binomial expansion. Okay, this suggests that, here's the biggie, the probability that the random value variable x is equal to one of the blue possibilities, little x. Remember, little x could be equal to 0, 1, 2, or 3. That's right there. Is this is p, the probability for success, and the probability for failure, 1 minus p. 1 minus 3/4 is 1/4. Okay, so let's say we wanted to know what the probability of drawing, I don't know, 2 blues is. Well, that means that little x is going to be equal to 2. And the probability of x equal to 2 would then be, 3 choose 2 times 3/4 to the 2 squared, I can't believe I said to the 2, times 1/4 to the 3 minus 2, or 1. And what is that? Turns out to be 0.4219, so about a 42% chance that we could get 2 blues. So that's how that works. Very nice, very simple, very easy. Okay, so this is what we just went over from the previous the previous example, sorry. And I just put it here so I could reference it while we're reading this. Consider a binomial experiment for which p is the probability of success and 1 minus p is the probability of failure. That's very important. P is always success, 1 minus p is always failure. If there are n independent trials, well, the number of trials in this experiment, the one we did before, was 3 because we spun the spinner 3 times, is given by probability of x equals r equals n choose r times the probability of excess to the r power times 1 minus p to the n minus r power. And r is always going to be integers. So this is just this. Same thing. It's just we have a general formula. This was specific for the experiment of the spinner that we had. Probability, this is called the binomial probability distribution function. Expected mean does not change. We learned that before. Or the expected outcome is equal to the number of trials times the particular probability, and that's for a particular random variable. And this is notation that we use. If x is the random variable of a binomial experiment with parameters n, number of trials, and p, probability of success, then we write x is distributed as the binomial, you can just say binomial distribution NP. Okay, what is this here? Well, this, I always put what it looks like on your formula sheet. Good news, it's exactly the same as we have here. No changes, and we already had learned about our expected outcome. And then what is this? Well, this is just talking about the calculator. To find the probability of px equals r, that the variable takes the value r, we use the binomial probability distribution function. That's to find a specific probability. If we want to find the probability that a particular value is less than another value, less than or equal to, that's a cumulative distribution function because we want to find the total amount of probability. And we'll see that clearly in this example, and there is only one example. So that's good. Okay. 72% of union members are in favor, thank you England and Australia, of a certain change to their conditions of employment. Okay, so 72% of union members are in favor. A random sample of 5 members is taken. So there's our n right there, 5 trials. Find the probability that 3 members are in favor of the change in conditions. So we are interested in the probability of, here let me move A over here, probability that x is equal to 3. So that would be, if it's just filling in right here, that will be 3. Oh no, I'm sorry, n is the number of experience. Sorry about that. So 5, choose 3. R is the number in question that we're interested. The probability of success is 72%, 0.72, times 1 minus 0.72, so that would be 0.28, to n minus r, so that's 5 minus 3, so that's 2. Oops, and this is 3. And we're all set. We can crank that on our calculator and you will see that that's 0.293. Now, you should remember how to do the find the choose thing on your calculator, but you can also do it very simply like this. Couldn't be easier. Menu, probability, distributions. And we're going to go down and we have a choice. The specific probability, binomial p, or the cumulative. If we're looking for a specific probability, which we were, x equals 3, then that's the one we use. We use the p for probability. Number of trials was 5. Probability of success was 0.72. And the x value is 3. And we hit OK. And there it was, 0.293 if you remember. Beautiful. Very simple. Very easy. If you didn't, you might have noticed that the x value was optional. If we got rid of that, I just want to show you, just so you know, it will give you everything. This is a probability of 0, 1, 2, there's our 3, there's our 4, and there's our 5. So it gives them all to you. That might be useful to you at some point. Okay, part B. The probability that at least 3 members are in favor of the change conditions. At least 3. So that means x could equal 3, 4, or 5. Okay? Well, one way to think about it is that is the probability that x is greater than or equal to 3, or the probability that of 1 minus the probability that x is less than or equal to 2. Okay? So you could figure out all of these individually, or you can think about it like this. So you would have to do this 3 times. Or our calculator will allow us to do this. Now this is less than or equal to, so this is the cumulative that I was talking about. Okay? So let's go back to the calculator and menu, probability, distribution, and we want the binomial cumulative, CDF. Number of trials, 5. This could not be easier. Probability of success, 0.72. Lower bound is indeed 0. And our upper bound, remember, was 2. That's what we're interested in. And we hit OK. And what I should have done is done 1 minus that. So I'm going to go up and copy that. I forgot to do that. Put a click here. Do 1 minus that. That's what I had written there before. And I get 0.862. So the probability of that occurring would be 0.862. I should say approximately for both of these, like I did there. And last thing, C, the expected number of members in the sample that are in favor of the change. Well, that's here. Expected outcome equals number of trials times the probability. That's very simple. So that's 5 times 0.72. which is equal to 3.6 members. Sorry for the length, 15 minutes. I'm stopping there. Becker is out.